So section 5.1 is going to discuss polar coordinates. Now, polar coordinates are a different way of regarding the point on the Cartesian coordinate plane. So this point, which we typically know as x and y, x distance from the y-axis, y distance above the x-axis, that can also be written in another way. If you want to specify, first of all, the radius that you are away from the origin, so that would put you on this circle here. Then you can also specify the angle here, and between those two, you can actually specify the coordinates of a point. Now, polar coordinates are useful in a lot of situations. They make certain things much simpler, and that's the motivation to use these things. But they don't make everything simple. So we'll have to pay attention to what we can do with them. The big thing that you should be getting out of this section is some relationships between x and y and r and theta. So section 5.1. One of the big ones is that r is the square root of x squared plus y squared. That's the radius. That just comes from the Pythagorean theorem when you apply that to this triangle. What else can we get? Well, if you play around, you get that x is r cosine theta and y is r sine theta. There's one last relationship that comes around from time to time as well, and that is tangent of theta equals y over x. That also allows you to solve for theta. Anyone solve for theta here? What would theta equal? The inverse tangent.
Inverse tangent.
Yep, thank you, inverse tangent. So these relationships should be things that you kind of keep close at hand and close in mind when you're working with some of these problems. Now, the big thing to get used to, first of all, is actually just plotting these things and understanding how those work. So let's do some examples. And keep in mind that when you're graphing things, they're always in the form of r and then theta, the radius, and then your angle. So they're going to give you r and theta. Now I'll start with kind of a gentle one, the point 4 5/3. Typically what I do is I find the angle first. So 5/3, that's going to be down into the 4th quadrant. And then a distance 4 radially away from the center. So let me just come up here and see if I can't grab this little point here. There we go. And put it down on our graph at 4 5/3. It's not letting me. Nope. All right. Thought this was going to work better. That'll be. No, it's not working. Anyways, I guess I'll just have to draw on it. It's going to be right here. So you got your angle of 5/3 and a distance of 4. 1, 2, 3, 4 away from the origin. Where things get a little trickier is when you have negative angles and or negative radius. Let's take a look at this one. If you've got a negative radius, that really changes your angle effectively by 180 degrees. So for instance, the angle 3 pi over 4 is right here along this line. If you go a distance of 5, that would take you out to here. But our distance isn't 5, it's -5. So instead of going this way, effectively you're going to add 180 degrees and move to the other side of the pole. The pole is the new name for the origin. It's where all these lines intersect. But there's your point right there. Lastly, let's take a look at -5 and -2/3. Once again, I'm going to start with the angle. So starting with the angle, which way am I going to go to move -2/3? Clockwise or counterclockwise?
Clockwise.
Clockwise, thank you. Now, you might want to take note of the fact that 2/3 pi is really 120 degrees. That makes it easier to go backwards 120 degrees. That'll put me at 240. So, okay, that's at 240. We've got a distance of not 5, but -5. So instead of putting a point down here, I've got to go to the other side of this graph and put a point right there. Okay. So there's kind of a quick review of plotting a few of these points. Comments or thoughts on those before I move on to the next set of examples. More plotting of points. Let's look at example B then. Now example B, you've got 4 different points. They're all a distance of 4 away from the origin. It's just that they're in different quadrants. And your job is to decide, well, what quadrant or what point is actually graphed. One thing that's unique about polar coordinates compared to rectangular coordinates, that is x and y, is that polar coordinates aren't unique. You can have multiple names for the same point, and that's a little different. It has some pluses and it has some minuses, but it's certainly something worth knowing. All right, so what I want you to do is try and look at these and decide what letter each of these go with. So let's take a look at the first one. You got to go an angle of pi/6, which takes you up here. But then instead of 4, we got -4. So what point should this take me to? A, B, C, or D? What do you think?
C.
C.
C. C it is. Excellent. Let's keep going. 4 and 5pi/6. Well, the good news is we don't have to deal with any negative angles or negative numbers. 5pi/6 takes you to the second quadrant. So I'm thinking that one looks like
B.
Okay, how'd that happen? Let's see. Huh. It's supposed to be B. Let's keep going. How about the next one? What'd you get for 4 and 7pi/6?
D.
Let's see, 7pi/6 would be 210 degrees, right?
Oh.
So that's gonna put you right here.
C.
C again. I'm just gonna copy that. I don't trust it to give me the letter and the font that I want. This next one's kind of tricky. So not only do you have to deal with a negative angle, but you get to deal with a negative radius as well, which I know for a long time in math, we said, no, the radius is going to be negative, but we're kind of using a negative radius now. So what do you think here? Where is this one going?
A.
Gonna vote for A? Okay. We agree with A? Let's take a look. -pi/6 is going to take you here, correct? And if we went a distance of 4, I'd go there. But is that what we got? Not quite. What's different about this? We got a -4. So instead of going to D, where are we going to go?
B.
B.
B. Yeah. So back to B. All right, while I fix this on B, maybe you can work on what the next one's going to be. No pun. And I'll clean this up a little bit as well. -4 and 5 pi over 6. Now, finally something different. Where should I start? What should I do first? I'm trying to figure out where this point is.
Find 5 pi over 6.
Thank you, Michael. Find 5 pi over 6. That's at B. Now, unfortunately, 5 pi over 6 is in this quadrant, but we got a negative angle, or excuse me, negative radius, so that doesn't leave us at B. What point do we end up at?
D.
D.
D. Yes, well done. Thank you, Kayla. Kayla put her answer in the chat. All right, let's keep going. Problem number 4, or excuse me, problem number 6 here, I guess. 4 and 11 pi over 6. That one's nice because you kind of just read it off. 11 pi over 6 goes into which quadrant?
330.
That's 330 degrees. So it's going to be in the 4th quadrant, making it which of these angles? A, B, or C, or D? D. Absolutely D. Kind of nice spin on that one. Problem number 11, or excuse me, not problem number 11, but 4 and negative 11 pi over 6. So when I went when I went positive 11 pi over 6, that angle ended up taking me into the 4th quadrant. So it left me this little 30-degree angle here. Now I've got to go the other way. So here, and that's going to leave me right here in A. So that's my angle, negative 11 pi over 6. I don't have to get fancy with that and adjust it because the radius is positive 4. So we'll just put in a nice big A. And back up and make that an A. Last one. -4 and 7 pi over 6. What are we going to get for that one?
A.
Christina says A. Do I have agreement with A?
Yes.
Yeah,
Yes.
that's it.
Yes. A it is. Nice. Now, the trickier one, and this one kind of reminds me of one of the problems I put out on your exam preview, is something like this, where they give you a point and then they ask you for other things. Like this is the point 1 and pi over 6. So I'm just going to pretend that this outer ring is really a distance of 1 away. So 1 and pi over 6 would put me right here. I mean, technically, I guess the way it's drawn, it's in here, but that gets too squishy. So now they ask you to rewrite this with a positive radius and a negative angle. So the thing that they're asking you to do is to go around the circle this way to get the angle. So instead of a positive 30 degrees, how far around would I have to go?
30 degrees in the other direction.
If you're going this way, if you're going clockwise, then that'd be a negative angle. And I don't want to just go negative 30 degrees because negative 30 degrees would put me right here at 330. I need to go a little bit farther. I need to go all the way around and then here. How far would I have to go? No one?
2 pi.
2 pi, I appreciate your enthusiasm this morning. 2 pi would take me right here. I need to stop a little bit short of that. It might be easier to think of it in degrees.
Is it 330 degrees?
Yeah, so 2 pi or 360 degrees would take me all the way around, but I want to stop 30 degrees short of that. So If
Plus
I,
360 negative minus 30.
yeah, so what you can do is you can take 30 degrees and subtract 360 degrees, and I'm not sure why my pen isn't working so good here, but there you go. You'd end up with minus 330 degrees. So the answer to the first part, and I'm just going to write it here, would be 1, because you wanted a positive radius, and negative 330 degrees. Or if it was in radians, 1 and negative 11 pi over 6. So that's part A. Part B, I want a negative radius and a positive angle. So I still want to end up at the same point. It's just that how I get there is going to change a little bit. So let me clean this up, start all over again. There's no getting around what to do for the first part. So for the first part, my radius has to be -1. So that's where I'll start. -1, and now I got to figure out the angle. Well, if I've got a radius of -1, then really my angle should take me to the opposite side of this circle. I should be over here someplace so that when I deal with my angle being negative, excuse me, my radius being negative, it takes me over to here. So in degrees, that'd be this much, 210 degrees or 7 pi over 6. 10 degrees, 7 pi over 6. And you can confirm that by just plotting that point for yourself. If I was to plot, come on. If I was to plot this point, which is equivalent to this one, you go to 210 degrees, move out to your radius of 1, but because this radius is negative, you move through the pole to the other side of the circle, effectively adding 180 degrees to get to your desired point. And when I do that, I'll end up right back here where I want to be. These can get a little tricky sometimes. So if you're having some doubts as I go through this, let me know. I'll be happy to try and approach things a different way, try and clarify myself, etc. Let's look at example C, the last one of these. We're back to a positive radius, but this time we want our angle to be between 2 pi and 4 pi. So currently our angle is pi over 6. That's okay. One thing I'll do to start with is I'll write down the radius. The radius is again 1. But pi over 6 doesn't satisfy this requirement here of being between 2 pi and 4 pi. So what I got to do is I got to come up with an angle so that when I plot that angle, I end up here. Here's my suggestion. Pi over 6 is putting us in the right spot. Well, what if I add 2 pi?
Pi over 6.
Pi over 6 plus 2 pi, right? Or let's think of it in degrees first. If you're thinking of it in degrees, you can take 30 degrees plus 360 and get 390 degrees. Yay. There you go. Now, 390 degrees in radians would be 13 pi over 6. But you can convert that as you will. 390 degrees or 1 and 13 pi over 6. Beautiful. Beautiful. Let me catch up with the chat here. Okay. How are we looking on those? Now, one of the things I said early on in this discussion was to remember how to convert between polar and rectangular. There was a couple formulas that you might want to write down. X equals R cosine theta, y equals R sine theta. And you can use those to directly calculate what certain polar, what rectangular coordinates are given the polar coordinates. This one is kind of easy to figure out without necessarily doing all that. In fact, the first two happen to be that way. So let's take a quick look at that. You got the point 6 and pi over 2. If you were simply to draw that, we'd start by finding my angle, which is 90 degrees, which is right up here. And then I got to go a distance of 6. So that radial distance would be 6. Now that puts you right on the y-axis at a height of 6. The x-coordinate there is 0. The y-coordinate there is 6. Beautiful. If you did take the time to calculate it, x equal 6 cosine of theta, cosine of pi over 2. Cosine is 0, so my x-coordinate is 0. Does anyone remember what the sine of pi over 2 is?
One.
1.
Yep. The y-coordinate at pi over 2 is 1. So there you go, x and y, 0 and 6. In a similar way, you could figure out where this point is. Negative pi would put you at negative 180 degrees. Negative 10 would put you back over on the x-axis. You'd end up with the point 10 and 0 would be that one. But if you're not really comfortable doing some of this stuff in your head, that's okay. You're not necessarily supposed to be able to imagine all of these things perfectly as you go through them the first time. So let's take a look at this last one here. The polar coordinates are 2.5 and 17 pi over 18. R and theta. So you need to take out your calculator. 2.5 times cosine of 17 pi. Was it over 18? Is that over 18? Yeah, I guess it was. Just feels odd. Over 18. So effectively 170 degree angle. And then y is going to be likewise 2.5 times the sine of 17 pi over 18. And you're just going to get decimal values. That's okay. I expect something in the second quadrant just based on those values, but that might not be so easy for you to see. I'll do it here because it's easier to see. Clear out some stuff. Now, I'm not sure that you noticed, but there's a key history underneath here so that if you're looking to see, well, what did I press? It's there. Let's change over to radian mode. Take care of that. And then exit. 2.5 cosine of 17 pi, which is right here, divided by 18. Negative 2.46. You're gonna have to pay attention to my math lab to figure out how many significant digits they want. I'm just assuming 2 at this point. And then sine of 17 pi divided by 18. That should be at least a positive number because we're in the second quadrant, sine is positive there, and it is 0.434, so about 0.43. Okay, how are we looking with that one? Doing all right? All right, making our way through these. Just a couple more. So this one's going the opposite direction. This time we're given the polar coordinates and you got to find the rectangular coordinates. So r and theta are 1.9 and 3.9 respectively. We got to think about where that would be. R and theta. Well, theta of pi would be right on the negative x-axis, because the angle of pi would put you right there, somewhere around, along the axis you get when you look at 180 degrees. So we're a little bit past there. So we're in the second quadrant someplace. I don't happen to know exactly where. That's okay. Let's just draw ourselves something in that second quadrant. And if you're not convinced that you should be in the second quadrant, you can take 3.9 times 180 over pi and get, a nice angle in degrees. That'll tell you where to graph this. So here's your y, here's your x. And actually, we've already solved this problem, so maybe I'm doing too much work here. X is our cosine theta, and y is our sine theta. And we've actually already got what we need. So let's just grind it out. That's going to be 1.9 times cosine of 3.9. This is going to be 1.9 times the sine of 3.9. And let's get some decimal values for each of these. I'm using little squiggly lines to represent approximately. I'm just going to do this one on my calculator. So 1.9 cosine of 3.9, negative 1.38, we'll call it. And I'll do the same thing except for the sine. And this one's negative 1.306, negative 1.31, I probably should round it to. But there you go. Those are your values. At least it landed in the third quadrant like I had anticipated. All right. How are those looking? Let's see. F. Last but not least, let's work the other direction. We're going to start out with rectangular coordinates and find polar coordinates. So for this last example, we'll start out with 1.4 and negative 3.2. What quadrant is this point going to be in? Right here. 1, 2, 3, or 4. Where should I draw that?
Four?
Yeah, 4. Because the y coordinate is negative and the x coordinate is positive. And that's only going to happen in quadrant 4. So let's draw it there. So 1.4 and negative 3.2. 1.4, of course, is your x direction. Negative 3.2 is the y direction. I would start off by finding R. So R is just going to come from the Pythagorean theorem. R is going to be the square root of 1.4 squared plus negative 3.2 squared. So I'll do this 1.4 squared plus negative 3.2 squared. But I still need to take the square root of that. My quick way to take the square root, once you've got the answer, is to hit the up arrow key and raise that to the 0.5 power. So hit the up arrow key to the 0.5 power. Should get something about 3. Yeah, I was gonna say 3.5. So about 3.49. Beautiful. So that's R. It's about 3.49. Last thing I got to figure out is what theta is. Now you can do theta in a couple different ways. It seems as though the book will accept a negative angle, or at least my math lab will accept a negative angle. The book generally wants a positive angle, but for my money, I would use these two sides to come up with the angle. Now, if I'm using this side and this side, what does that imply? What function?
Tangent.
Tangent. So tangent of theta would equal negative, or excuse me, 1.4 divided by negative 3.2. So you still have a negative. That means theta is going to be the inverse tangent of negative 1.4 over 3.2. That's going to give you a negative angle. It's going to give you something down here. So if that's okay for the problem, that's fine for us. Second inverse, negative 1.4 divided by 3.2. That's in radians. So negative 0.412. You could get another answer in the second quadrant, but that wouldn't be the right quadrant for these coordinates. If you want this angle to be between 0 and 2 pi, then that is a positive angle. You could just add 2 pi to that angle. So instead of going a negative 0.41, you could go positive 5.87. 5.874. Both of them take you to the right spot.
What if the calculator was in degrees?
Great question. So let's do it in degrees. Let me put it in degrees. It's still going to give me a negative angle. I'm trying to think about what negative angle that would be. I'm not even going to pretend to guess. So negative 23 degrees. But if I wanted, instead of going negative 23 degrees, if I wanted a positive angle, do you know how I would get that positive angle? What could I add to this?
2 pi? No, 360.
There you go, perfect. 2 pi is the correct answer for radians, and 360 is the correct answer for degrees. So a couple possible answers. One would be a negative 23 and change. The other one would be 336 and change. So it depends on what the problem's asking you for as to which one you'll give. Okay, wow. That was a good one. So we're going to play around with the graphs of these polar equations that we're working with. And it's helpful to know roughly what to look for and what to expect when we're graphing some of these things. Because sometimes when you plug them into your graphing calculator, you might have the settings wrong somehow, and you don't get what you expect. For instance, if you have something of this form, r equals a sine theta or a cosine theta, you're going to get a circle. Or in other cases, you get this heart-shaped graph called a cardioid. Now, in still other circumstances, you get something that kind of looks like a cardioid, but it's actually what's called a Limason. And it could be a Limason with or without an inner loop. Now, the inner loop, in this case, is right here. That's this part where the graph passes back through the pole, does a little loop around on the inside of this figure, and then continues on. Now, the way you graph these things and the way your graphing calculator or Desmos graphs these things is it chooses a value of theta, plugs that value of theta into whatever equation you have, plots a point, and then chooses another close value of theta, maybe incrementing by just a little bit. So maybe by 1 degree or 0.5 degrees, depends on the program and depends on the settings. But to get used to these graphs, let's take a look at the little Desmos link that I sent you. Now here you've got r equals a times cosine of theta. And that's just a nice graph that's centered on the x-axis. What I want you to do is I want you to play around with this value of a and just slide it some, slide it all the way up to 2 maybe, and bam. And what you see is a circle centered at 1 and 0 along the x-axis. So one thing you can pick up from this is that the radius of this circle is half of what that value a is. So a is your diameter, your radius is going to be half of that. Now along the slider, you can go all the way down to 0, but I also allow you to use negative values. And there's something interesting that happens when you pass through here and get a negative value. So down to 0, and then bam. All of a sudden on the left-hand side, there's your graph. Now, why is that? Well, the reason for that is because all of a sudden you're switching sides of the circle. If you remember when we were plotting r and theta, that if you had a negative radius, then that meant your graph was reflected through the pole or the origin. So shifting things to a negative just shifts the graph, reflects it around the other side of the origin. Now, that's r equals a cosine of theta. So those are circles along the x-axis. Before I turn this graph on, can anyone make a prediction for r equals a sine of theta? What would you expect from this graph?
It would reflect up and down.
Reflect up and down. These are going to be circles along the y-axis. Perfect, Reagan. So up here, you've got a nice circle around the y-axis. And as you pass through 0, you get some negative values. It's still a circle. It just happens to be below the x-axis, still along the y-axis. So those are circles. Now, there's other graphs that are kind of cool and fun to look at. So let's shut that off and then examine the roses. Now, the roses are something that you should have picked up on a little bit in my other video. I'll start out with n equal 2 and r equals effectively sine of 2 theta. Now, the one interesting thing to notice is that you've got 4 petals for sine of 2 theta. And here is 2. But let's bump that up from 2 to 3. And this is odd. We added a little bit more to n, so we had n equals 3, but now we have less petals. And then when we go to 4, all of a sudden there's 8 petals. And then 5, there's 5 petals. And so on. 12, 7, 16, 9, and 20. So what's the pattern here? What's going on with these petals? How could I predict how many petals that they're going to be?
Odd and even number.
Yeah, odd and even numbers. So what happens with the even numbers, heck, Matt?
Even number, I think, will double itself. Like
Exactly.
instead of 4.
So the number of petals is going to be twice what this even number is. What happens with odd numbers?
It just
Stay-
repeats itself.
Just stays the same.
Just stays the same. So
Yeah.
odd numbers, yeah. If it's 5 or 7 or 9 or whatever, as long as it's an odd number, that's going to tell you how many petals there are. But for the even numbers, it doubles. And that's true whether or not you're dealing with sine or cosine. The difference is that cosine, this first petal, as I like to call it, is going to start right on the x-axis. You're going to have a petal that surrounds the x-axis. The top and bottom half are going to be parallel to that. So you're always going to have that petal there. The rest of the petals are going to be spread evenly throughout all the angles. So there you go. It still follows the same even odd pattern that your sine did. Okay, let's take a look at some more here. Let's take a look at cardioids. Cardioids have this form. This one happens to be written with sine of theta. We can take a look at what happens with cosine of theta. And if you adjust this, you'll see that when you have a sine of theta, you got something that's reflected, or excuse me, that's symmetric with respect to the y-axis, or the imaginary axis is what we'll call it in section 5.3. But this vertical line here, so sine theta gives us something in this direction, whereas cosine of theta is going to give us that same kind of shape, except along the x-axis. Now, the name of this shape comes from this graph right here, because what does that look like? Something you send to somebody on Valentine's Day, right? A heart, hence the name cardioid. Now, the thing about cardioid is that this is the graph that you're going to get when you have something of this form. You could also have it, I could also have written this as C minus C times sine of theta. So in other words, these two numbers have to be the same. Now over here and down below, I've got it factored out. But basically, you're going to get this cardioid shape when these two are the same. And finally, the last shape that it's helpful to be familiar with is what's called a Limason. I can't give you any background or information about the name Limason. I just know how to pronounce it. Now, in contrast to our cardioid, you've got this little inner loop. And if you play around with the values of P and Q long enough, you'll figure out when that inner loop happens. So let me see. Let me make the value of Q a little bit bigger, and my inner loop gets a little bit bigger. I'll make the value of Q smaller. I can make that inner loop disappear. And now all I've got there is a dimple where I used to have a nice inner loop. If I actually make this exactly 0.9, then that's a cardioid. But we can go a little bit farther. And now I've got another inner loop. Basically, you're going to get an inner loop if this number Q is bigger than the number P. That's what you're going to get. So that information is summarized here. And let's see if we can't use that to try and figure out some of these graphs. So this first one here says, for a positive real number A, which of the following polar equations is a circle with radius A and a center at A and 0? Now A and 0, that's going to put something along the x-axis. So there's two of these that I can eliminate right away. I can eliminate this one. Oops, not that one. I want to eliminate the sine graphs because sine graphs are going to put things along the y-axis. So let's eliminate our sine graphs. And now we have a choice between negative 2a cosine of theta and positive 2a cosine of theta. Well, it's going to be the positive 2a cosine of theta that's going to put your center along the positive x-axis. If I chose this one, I'd have a center at negative a and 0. One of the nice and easy things about, or one of the nice things, and I won't necessarily say easy things, but one of the nice things about polar equations is that they make some things really simple. For instance, they might be asking you to identify this graph r equals 9. Well, to figure what that graph is, unless you happen to know this, you might want to look back to our notes from section 5.1 and realize that r is equivalent to the square root of x squared plus y squared. So I'm going to write that here. Square root of x squared plus y squared equals 9. And that's kind of an ugly looking equation. So let's see if I can't clean it up a little bit. And the way I'll clean it up is I'm going to square both sides. On the left-hand side, I get x squared plus y squared. On the right-hand side, you can leave it as 9 squared, or you can write it as 81. I'm going to leave it at 9 squared for my own reason that I'll share with you in a second. But does anyone recognize what this equation represents? It's a circle. Radius. What's the radius of that circle? Does anyone know? It's
9.
It's 9. Now, the reason I left it as 9 squared is because that shows you what the radius is. There's nothing wrong at all with writing x squared plus y squared equals 81. It's just if you write it that way, then you're going to have to realize, oh, the square root of that is 9, and that's my radius. Center at 0 and 0. But that's a pretty simple equation, right? I mean, certainly it's a little simpler than x squared plus y squared equals 9 squared. One of the cool things about Desmos is that you can graph in polar coordinates pretty easy. All I would do is just type in r equals, now I'm going to do r equals 1, because if I did r equals 9, it wouldn't fit. Actually, you know what? We can do this. There we go. Now let's bump r equal up to, yeah, whatever you want. But r equals a number is just going to give you a nice, pretty circle. And that's a pretty easy equation to work with. So polar coordinates have a lot of things that they do, some of which are to simplify otherwise complicated equations. They don't always do that. Some equations in polar are more difficult than they are in rectangular coordinates. Stuff like this, theta equals pi over 3. This is just a graph of a line, a straight line that runs through the origin. So let me write down theta equals pi over 3. And we'll work with that. Now it doesn't specify what r is, so it's just the line that runs through the origin at this angle. To understand this perhaps a little bit better, and maybe in terms of polar coordinates or rectangular coordinates, I can take the tangent on both sides. So that give me tangent of theta equals,
just need to clean this real quick.
Zach, if you can mute yourself.
You're
All right,
good.
maybe I'll help with that. There we go. tangent of theta is going to be, tangent of pi over 3 is going to be square root of 3. And you may remember that the tangent of theta was y over x. And why did I write square root of x there? I don't know. There we go. Little roll on Photoshop, square root of 3. Finally, if I multiply both sides by x, I get that equation. Hopefully you remember this as y equals mx plus b. B would be 0, so you just got a line running through the origin, and the slope of that line is the square root of 3. Anytime you have theta equals some angle, it's just going to be a line that runs through the origin. Here's a nice friendly one that we can work with. R sine of theta equals 6. R sine of theta equals 6. There we are. Do you remember your substitutions? What is R sine of theta equal to? What can I replace this with in terms of x's and y's? Which one was that?
Why?
Yeah, so it's y equals 6. So y equals 6 is kind of a nice friendly graph, right? Just 1, 2, 3, 4, 5, 6. It's just going to be a horizontal line at that height. I'd prefer this equation to this one. Not everything in polar coordinates is actually prettier or nicer than what you get in rectangular coordinates. In the same way that you had r sine theta equals 6, we could also look at, say, r cosine of theta equals 3. What would that equation look like?
X equal 3.
X equals 3. And hopefully you remember that the graph of x equals 3 is going to be a vertical line like this. That kind of information is going to help you with some problems that you'll see in the homework. So let me pause here for a second to see if you're doing okay on these things so far. No worries, concerns? Okay.
Maybe just one more example.
Sure. How about a bunch of examples, really? Let's see. Yeah, let me go down to this one, because this one would be one of your homeworks. And I guess what we've been doing in the last couple examples is going back and forth between polar coordinates and rectangular coordinates. So the one that I have circled there is the one we're going to do next. Now, I really don't have a good idea of what that graph would look like. So sometimes it's helpful to put these back in X and Y form. To do that with this problem, what I would first do is I'd multiply both sides by 1 minus cosine of theta. 1 minus cosine of theta. Can anyone see an advantage in doing that? What's that going to do for me? Well, on the right-hand side, I'll get some simplification, right?
Get rid of fraction.
Yeah. So on the right-hand side, those two terms cancel each other out. So hasta la vista. On the left-hand side, I'm going to distribute the r. And I'll have r minus r cosine of theta equals 20. Now let's start working towards X's and Y's. But are we okay with this first step?
Yes.
Thank you.
Yes.
This is x squared plus y squared. That's x. And, you know, I'm just not a real big fan of that square root. And in fact, you're going to have to get rid of that square root in order to get this problem right. So what you could do is move the x to the other side and get the square root of x squared plus y squared equals x plus 20. Notice that when it changed sides, it changed signs. Finally, I can square both sides of this. So if I square the left-hand side and square the right-hand side, on the left-hand side, you're going to get x squared plus y squared. On the right-hand side, I'll get x squared, and I hope no one says x squared plus 400. There's a missing term in there. Do you know what that term is? If you FOIL it out, you can see it. X
Would it
plus,
be 20x?
you're halfway there.
40x.
40x.
Yeah, because when you FOIL it out, you get that 20x term twice, right? Here and here. So my trick when I do these things, when I FOIL out stuff like this, is I borrow this exponent. I'm like, okay, it's going to be 2 times this times this. So 40x. If I subtract x squared from both sides, I'll end up with y squared equals x squared plus, oh no, I don't have an x squared anymore, do I? Y squared equals 40x. Plus 400. And that's not bad. You probably, let's see, probably you'd solve for y there. But the problem's not asking you to solve for y. The problem's asking you to get 0 on one side. So the last step here, says complete the general form of the equation using rectangular coordinates. 0 equals. So they want 0 on one side. So it'd be 40x minus 400 or plus 400 minus y squared would be the correct or a correct form of that final answer. So, whew. All right. Let's do one more kind of in that same spirit, and then we'll identify a few graphs, and then I'll put you in your little breakout rooms. So this next one right here, r equals 10 plus 20 sine of theta. I see some people doing some pretty wild things on this kind of problem because I can't just put a y here. Why not? What am I missing that won't allow me to put a 20y here?
R.
R. I'm missing an R. So the idea in doing this one is to introduce that R. I'm going to multiply both sides by R. And when I do that, I'll get R squared equals 10R plus 20R sine of theta. Now I've got substitutions for everything. On the left-hand side, well, let's see, let me do this on the right-hand side first. R is the square root of x squared plus y squared. This much is my y, so that's plus 20y. And if I were to square this, I'll get x squared plus y squared. Okay, now that's a pretty ugly equation. Yeah, at least as it stands. Let's see what they ask us to do here. Identify the polar graph. Oh, yeah, no wonder why it's an ugly equation. Yeah, this equation in polar is a lot nicer than it is in rectangular coordinates. And its graph is actually kind of beautiful. So, I mean, you can play with this some more. It's not going to make this equation very pretty. I guess if I had to play with it, I'd move this to the other side and I'd square both sides to get rid of this root. That'd give me x's and y's to the 4th power. Ugh, it'd be a bummer. But I didn't pay attention to the instructions. We're just to identify the radical. Now this trick here, though, of multiplying by r is a good trick, because sometimes you need to do it when you're converting from rectangular to, or I mean, polar to rectangular. So it's not a waste. And it brings us to the last kind of problems here. You're asked to identify these things. So let's spend a little time identifying them. And the trick is to keep these things in mind. So our equation was 10 plus 20 sine of theta right here. So that's in the form of a Limason. But the question is it a Limason with one loop, or excuse me, they call it a one loop Limason. I just call it Limason without a loop and Limason with a loop, or an inner loop. And what you got to look at is the values of A and B. In order for you to get an inner loop, this number here has to be bigger than this number, A. So A and B are both positive, but A is smaller than B. That's what it's telling you. If A is bigger than B, then you're going to get a Limason without that inner loop. So let's take a look at what we got again. Come on, there it is. What do you think? Is this going to have an inner loop or no?
Yes.
Yeah,
Yes.
because that's bigger than, that's 20 is bigger than 10. Now the good news is you can check these pretty easily on a graphing calculator or on Desmos. Now I don't know if you're always going to be able to use Desmos in whatever future courses you're in. So let me show you how to do this on a graphing calculator. I'm going to clear this out. The first thing we're going to do is we're going to change our mode. And for the first time in this course, I'm moving away from function. I'm going to come all the way over here to polar. And when you're done with that, just clear or quit to get out of that. But now we're in polar. When you take a look at your equation editor, it gives you something much different. You're like, well, wait a minute, what's that? And in fact, when you type the X key, it doesn't give you X anymore. It gives you theta. So, wow. We want to look at the graph of 10 plus 20 sine of theta. Like I said, in this mode, when you type the X key, it gives you a theta there, which is very convenient. For your window, what I would suggest is that you set up your values of theta between 0 and 2 pi. What your calculator will do is it's going to break this up into a bunch of little steps. It's going to start out with theta equals 0, plug that into your equation, find a point and plot it, and then increase the value of theta by, in this case, 0.1. And this you can keep on plotting points until we get up to a maximum of 6.3. Now, sometimes I use 6.3, sometimes I'll use 2 pi, but there's some little snafus and technical difficulties here. You won't quite get that last point. So sometimes your graph will fall short. As far as the rest of the settings are concerned, it's tough to predict what you might need. So the easiest thing for you to do is hit zoom and then the number 0. Zoom and then 0 will make your calculator adjust things so that it fits. And there you go. There's your Limason with an inner loop. And see, it didn't quite finish off that graph there, which I find annoying. Let me see if I can adjust my window. Oh yeah, that's because I left it at 2 pi. Let's go to 6.3. Let's see if that does it. Yeah, that one does it. Beautiful. Whew. Okay. How are we looking there? Are you okay with the graphing? I mean, you can always double check these things on decimals as well, but it's probably a good idea to be able to adjust your graphing calculator to get these as well. I'd recommend it. All right, that'll do it for our little bonus section, bonus material.